Good evening, class. I'm Mohit, TA of the course Quantum Hall Effect. This course is being offered by NPTEL year 2025. This is the class 8 of this this semester, and the learning objective of today's class is to help you understand the origin and consequence of the band inversion in the mercury telluride and cadmium telluride and how it leads to the topological states. So the learning objective of this class mainly it is the help you understand the origin and consequences of the band inversion in mercury telluride HGTE compared to CDTE cadmium telluride, and how it leads to topological states. Topological states. Okay. So specifically, it will build your following skills. Build from this class. The first one is we will be recognizing a normal versus the inverted band order or inverted band structure in semiconductor. So recognize the normal versus inverted band structure. Okay, the second will be understanding how massless Dirac fermion arise at the interface of inverted mercury telluride and normal cadmium telluride material. Second will be understand arise at the interface of inverted mercury telluride and normal CDT material. And then through this class, you will be learning to use and analyze BHZ model. Or this BHZ model, BHZ is Bunwig, Hughes, and Zhang model, BHZ, for topological insulator. And then you will be relating quantum well thickness to the topological phase transitions. To topological phase transitions. Okay, so having said that, I'll start the class and we'll put forward the first question, which is based on recognizing the normal versus inverted band structure. So, question number one is for the mercury telluride and cadmium telluride superlattice structure, consider the spin split bands, namely gamma 6 S type and gamma 8, which is P type, and which are Kramer's pairs. And then identify the conduction band and the valence band with these symmetries for mercury telluride and cadmium telluride. So that is your question. Let me just write it for the GTE and CDTE. Superlattice structure. Consider the spin split bands, namely gamma 6, which is S type, and gamma 8, which is P type, and which are Kramer's pairs. Then identify the conduction and the valence band with these symmetries. For mercury telluride and CDD. Yeah. So let's unpack this problem carefully. So in this problem, I'll be explaining the symmetry levels, orbital character, degeneracies, why the ordering is different in cadmium telluride and mercury telluride, and how that shows up in models and how you test it experimentally. All those things I'll discuss. So let me discuss about the crystal symmetries background. Okay. So both cadmium telluride and mercury telluride crystallize in zinc blend structure. Mercury telluride crystallizes in zinc blend structure, right? Which is face-centered cubic FCC with 2 atoms per basis. Right. And at the Brilliant zone center, which is what we call the gamma point, electronic states are classified by the representation of the crystal symmetry. Commonly, we use the labels like gamma 6, gamma 7, gamma 8. These labels encode both orbital character, whether it is S-like or P-like, and total angular momentum or spin coupling. These labels encodes information of both orbital character, so that is P S like or P like, and total angular momentum or spin coupling. Okay. So now if I ask you what does this gamma label means, what is the physical context of it? So what is physical context of gamma label? So the gamma 6, which is primary S-like state, spherical, and L quantum number L equal to 0, and with spin half it is twofold degenerate Kramer space. And this states normally forms the conduction band in many third to fifth and second to sixth semiconductors. So the gamma 6, which you know, is primary S-like states. Spherical, because S orbital is spherical, and it has quantum number L is equals to 0. And generally forms the conduction band in third to fifth and second to sixth semiconductors. Then comes gamma 8. This is primary P-like with L quantum number L equals to 1. Primary P-like with L is equals to 1. And this states coupled with spin to give J is equals to 3 by 2, because for S it is total angular momentum will be J plus S, so your spin will be half only, so you can have two Kramer space. But here you have L is equals to 1, and since it can S can be plus minus 1 half, so J will be, if you say L plus S, your absolute J value is 3 by 2. It's then it's fourfold degenerate, right? At gamma points, two Kramer pairs. These are the heavy hole and light hole states, and which are degenerate at the gamma in the absence of strain or spin splitting. So your J is equals to 3 half here, and in that case your J is half, right? Because J is equals to L plus S. Okay, so that is about the gamma 8. Now, if you ask about the gamma 7, that is the spin orbit split p state with your total J quantum number to be half, and the split of band. This usually lies lower in energy than gamma 8 by spin orbit split also. Important point to note here is that whatever I'm writing, the S-like or P-like, it's shorthand for the dominant orbital character of the Bloch wave at the gamma point. Hybridization do exist, but this picture is basically useful for the starting point. Now, coming to the question part, which is normal ordering of the cadmium telluride, which is conduction band and which is valence band. And so CDTE is a normal semiconductor. Right? So it is a normal semiconductor. Conduction band minimum occurs at gamma going to gamma 6 S like, and valence band maxima occurs at gamma going to gamma 8, which is P like. So conduction band minimum what we call CBM will be at gamma going to gamma 6 S like, and valence band maximum will be at gamma going to gamma 8, which is P like. There J is equals to 3 half. Okay? And in symbols, if you write, energy of the gamma 6 will be greater than energy of the gamma 8, because conduction band is higher in energy than the valence band. So the S state lies above the P state, and electron occupies gamma 8 states at the top of the valence band. Exciting an electron moves it into the gamma 6. So you have your gamma 8, let's say gamma 8, and you have your gamma 6 here, right? That's what it essentially means. So your electrons from gamma 8, the top of the valence band, gets excited into the bottom of the valence band gamma 6. And physically, cadmium and telluride are lighter, weak relative stiffness effect. So the spin orbit splitting and orbital energies keep the usual ordering basically. And P derived valence band below, S derived conduction band. What are the consequences of the cadmium telluride? There is a direct band gap at gamma. Optical transition allowed between gamma 8 and gamma 6. What does this direct band gap mean? So you have this thing and this thing, right? You can have band gap like this. This is your k axis and this is your energy. One kind of thing. Another you can have it like this and like this. Right? This is another kind of thing. So these where conduction band minima and valence band maxima lies on top of each other. This is known as the direct band. Okay. Here conduction band and the valence band maxima, conduction band minima lies at different k values. So this will be at k1 and this will be at k2. So this is known as indirect band gap. For direct band gap, the optical transitions are allowed. For indirect band gap, there are dissipations. Now, this is about the cadmium telluride. Now, let me discuss about the inverted ordering of the mercury telluride and what changes, because the crystal structure is same, right? But something has changed. That's why you are seeing this inverted ordering. Inverted ordering of mercury telluride. What changed? So if you ask me what has changed in the mercury telluride, so gamma 8 lies above gamma 6 at gamma in this case, and thus gamma 8 becomes the states at a higher energy and gamma 6 lies lower. If you see here, gamma 6 in the top, gamma 8 in the bottom. But in case of mercury telluride, since J is equals to 3 half, your angular quantum number L is 1, right? And because of that, your gamma 8 lies above gamma 6 at gamma point. Thus, gamma 8 becomes the state at high energy and gamma 6 the lower. That's the key difference. So here, energy of gamma 6 was greater than energy of gamma 8, but here energy of gamma 6 is lower than energy of gamma 8, and the S like state has been pushed down below the P like state. This is called the band inversion. Here S like state has been pulled down, pushed down below the P like states. And this is known as band inversion. And why it happens? Now I ask you, because mercury is heavy atom with strong relativistic effect. Why do it happen? Because mercury is heavy atom with strong relativistic effect. And of course, if it's a heavy atom, then the spin orbit coupling we know that goes as J to the power 4, which is J in the atomic number, and strong spin orbit coupling. This relativistic contraction and energy shifts of the mercury orbitals and their hybridization with telluride changes the relativistic energies. Like the S state is pushed down related to the lighter second or sixth compound, and which produces the band inversion. This leads to band inversion. So the detailed mechanism includes the band hybridization, strong atomic spin-orbit coupling, chemical bonding, differences between mercury telluride and cadmium telluride. That's the detailed mechanism basically. So if I draw the band here, so in this case, for example, here you had your gamma 6 and you had your gamma 8. But in this case, your this is your gamma 8 and this is your gamma 6. And this axis is your energy. This axis is your energy. This is for CDTE. This is for HGTE. Right? So these are the reasons why it happens. So detailed mechanism I can write. Detailed mechanism includes band hybridization, plus strong spin orbit coupling, strong atomic spin orbit coupling, plus chemical bonding difference. So what are the consequences in the bulk mercury telluride? So then the bulk mercury telluride is zero gap or semi-metallic at gamma point because the inverted band touches depending on exact details. So there is no positive direct gap like cadmium telluride. But when you make heterostructure like mercury telluride quantum wells between the cadmium telluride, this inversion is the origin of topological phase which is quantum spill hole. Or the consequences in bulk HGTE bulk is zero gap or semi-metallic. But when you but when you make heterostructure of HGTE quantum wells between CDTE, this inversion is the origin of topological phases like quantum spin hole. Yeah, this is good. But now, if I ask you, how would you know that which one is which? Like, what are the experimental signature? First is optical absorption or photoluminescence. Because CDT is a direct band gap, so it shows a transitions from gamma 8 to gamma 6 because gamma 8 lies in the lower energy. But mercury telluride lacks the normal direct gap and shows inverted signature. So if you do optical absorption or photoluminescence, CDTE shows a clear direct gap transitions at gamma, but at GTE lacks. Second is angle resolved photoemissions, RPES. You can directly map the band energies at gamma and can see inversion. just directly maps band energies at gamma. You can show inversion. Or the other thing you can do, the cyclotron resonance or effective mass measurements. Electron versus hole effective mass and sign differs for mercury telluride, and which shows anomalous small negative gap behavior near gamma point. Other one is transport in heterostructure. So in HGT and CDTE wells, quantum wells, there is existence of the topological state that has been shown. When the quantum well is thick, this is another experimental fingerprint of the inversion. So this is about this question, which we discussed what are the gamma points, what does this gamma 6, gamma 8, these number mean. Then we looked at the band structure of the CTTE, cadmium telluride and mercury telluride, and we showed what are the difference between these two and how that leads to these topological states and the band inversion. Okay, that's good. Now, in the second question, which I put forward, is how massless Dirac fermion arise at the interface of mercury telluride and cadmium telluride superlattice structure. Yeah. So I'll just put forward the physical picture of it first. Okay. So a mercury telluride and cadmium telluride heterostructure can be constructed so that mercury telluride region is inverted. Basically, gamma 8 is above gamma 6, while the surrounding CDT is normal. So you make like CDTE, then you have your mercury telluride HGTE, and then surrounding you can have CDTE essentially. So this is normal. This is also normal, but we know this is inverted. This is inverted band because gamma 8 lies above the gamma 6 here, right? So that produces a special domain wall in the effective mass parameter that appear in the low energy Hamiltonian. The sign of the mass term changes across the interface. Here, the sign of the mass term you define basically on very rough saying, sign of mass term is sign of energy of gamma 6 minus energy of gamma 8. So for CDTE, sign is positive, and for HGTE, sign is negative. So at the interface, there is a sign change of the mass. At such a domain wall, where there is a change of this mass sign, A bound state appears whose dispersion along the interface is linear, gapless. A massive Dirac, massless Dirac fermion basically. In this two, in 2D, this gives helical edge states. This is what we call Jackie-Rabi mechanism, especially varying mass my with a sign change binds a zero mode that disperses linearly with a momentum along the interface. I'll show you the simple interface, so simple also. So if you see at this interface and at this interface, your M is changing. Sign of M is changing. What it does? So these are like a domain walls, right? And these domain walls a bound state appears whose dispersion along the interface is linear. That is gapless. And this gives a massless Dirac fermion. In 2D, this gives helical edge states. I will explain you what does helical edge states mean. Okay. In normal quantum hole, when you have your one probe at chemical potential mu left, mu right, then your edge state goes like this, right? This current goes like this, and then corresponding like this. So these are like all the spin up or spin down, they both are moving in the same direction. This is known as chiral edge, and you will get the conductance if there are n number of such states. Your conductance will be n e square by h. Simple. These are chiral edge. But there is another thing which can be possible. This is mu L, this is mu R. Your state is like this. Your up spin is going in the right, but your down spin is going in the left. Similarly, your up is this side, and your down is this side. This is your down spin, your up spin. These type of edges are known as helical edges. So that's the physical picture. But if you want to see the like BHZ view also, BHZ model view, I can just explain that one also. So there's a simple derivation I'll just keep. Okay. So I'll start from a 2 by 2 part of the BHZ models. The BHZ model I will cover in the next question. So near the gamma point, the Hamiltonian can be written in the continuum form as the Dirac Hamiltonian, which goes like A is constant and then Kx sigma x plus Ky sigma y, and then there is a mass term My sigma z. And this My is something which changes sign at the interface, right? Where My changes sign at the interface. Example, m less than 0 in, of course, mercury telluride, because your energy of gamma 8 is more than gamma 6, and m is has the sign of energy E6 minus E8. And m greater than 0 in CDT. Now we look for the solution which are localized in the y and plane wave in the x, and the substitute kx as a parameter and replace ky as the minus iota del by del y. Then we look for the domain wall my, which admits a solution localized at the interface whose energy depends linearly on the kx, of course. So your E at the as a function of kx will be approximately plus minus a kx. That is a massless Dirac dispersion, right? If it, because it can has positive and negative energy both, and at 1 kx, and at the same time they are gapless, right? So this gives massless Dirac dispersion. And the plus minus corresponds to the two Kramer pairs, basically. Opposite spin propagation direction for a time reversal symmetric system. So if one spin is going in the right, the other downspin will go in the left. That these are the Kramer pairs. So the corresponds to the two Kramer's pairs. Opposite spin propagates in opposite direction. And the physical consequence of it is like those interface modes are helical, like spin tied to propagation direction, and are robust as long as the time reversal symmetry is preserved. This is the physical consequence. So these helical modes spin is tied to the propagation direction, and are robust to the impurities and all those things in the system as long as the time reversal symmetry is preserved. Yeah. Now I will move on to the third problem, which is in the Brevin Hughes and Zhang model. We'll make a simplification of energy E of kx equal to 0, which has symbols have usual meaning in the context of the BHZ models. And now we'll find the eigenvalues of the BHZ Hamiltonian. And we'll express our results in terms of the coefficient A, B, and M, which we have discussed in the class, the professor has discussed in the class. So those things. Yeah. Now, Zhang model. Make a simplification of energy kx equal to 0, where of course symbols have the usual meaning in the context of the BHZ model. And now find the eigenvalues of the BHZ Hamiltonian, and we'll express our results in terms of the coefficient A, B, and M. Yeah. So we'll use the usual 2 by 2 block for one spin block of the BHZ model. The full BHZ is 4 by 4, but block diagonal with time reversal partner. Right? So the HK Hamiltonian will be A times kx sigma x plus ky sigma y plus m minus bk square times sigma z, where k square is kx square plus ky square. And now we set ek equal to 0 as given in the problem. So this is of the form hk is equals to dk dot sigma, where d is akx, aky, and m minus bk square, and sigma is the Pauli matrix. In that case, the eigenvalues the eigenvalues of a Pauli vector Hamiltonian are ek is equals to plus minus dk a square k square plus m minus bk square whole square. So the energy bands will be plus minus under root of a square kx square plus ky square plus m minus b kx square plus ky square the whole square. And so if I have to give remarks on it, so at small k the gap is 2 times modulus of m, right? If bk square is negligible, the sign of m determines the band ordering at gamma point. If m is greater than 0, it's normal ordering. If m is less than 0, it is inverted ordering, topological phase for suitable b values of b, right? And the parameter b, capital B, will modify how the mass changes with the k quadratic direction. The gap can close for certain parameter values, that is at the topological transitions, right? So if I have to write these ones, I'll write at small k the gap is 2 times modulus of m if bk square is negligible. And the sign of m determines the band ordering at gamma point. M greater than 0 is normal ordering, and m less than 0 is inverted ordering, which is topological phase for suitable B. And the parameter B modifies how the mass changes with the K. that gives the quadratic corrections. The gap can close. For certain parameter values. Example at the topological transition. Okay, so this question is over. Now I'll take the final question, which is question number 4. Show a schematic energy band diagram for a mercury telluride slab of thickness D, sandwiched between CDTE structures. Show the scenario corresponding to D greater than DC and D less than DC, where DC is the critical thickness where the electron hole subband merge, and what is the value of DC? Okay, DC implies critical thickness where electron and hole subband merge, and then what is its value? So that's the question. That has multiple actually sections to it. So I will go with the physical explanation. Right. So a mercury telluride quantum well sandwiched between CDTE barrier has quantized subband derived from the bulk gamma 6 and the gamma 8 band that we have discussed, right? So as the mercury telluride well thickness D is varied, the relative ordering of the lowest electron subband even from gamma 6 and the highest heavy hole subband H1 from gamma 8 changes. For thin wells, when D is less than DC, the ordering is normal. So E1 is above H1, trivial insulator like a normal semiconductor. But for thickness, for D less than DC, the ordering is normal. What does I mean? E1 which is coming from gamma 6 band is above H1, which is coming from gamma 8 band, right? And this leads to the trivial insulator, normal semiconductor. But for thick wells, but for thick wells, D greater than DC, the order becomes inverted. So this is for D less than DC, but for thick wells, D greater than DC. The ordering becomes inverted, even dips below H1, what we call the band inversion. This leads to the inverted band ordering. And that leads to the 2D topological insulator. And that gives the quantum spin Hall phase. So at the critical thickness D equal to DC, the even in H1 subband crosses and the gap closes at K equal to 0. At D equal to DC, the even and H1 subband cross and the gap closes at K equal to 0. We can of course draw the schematic. Okay, so first one schematic I will draw. Schematic for D less than DC, which is normal. What will happen in the normal? Your CDTE gamma 6 will be in the lower and CDTE valence band gamma 8 will be in the top. One second, I'll just reconfirm whatever I'm saying. Just a minute. Yeah, so whatever I've said is right. I just had a doubt. Just get it clarified. So D less than DC, this axis is your energy. You have your CDTE valence band, gamma 8, CDTE conduction band, gamma 6 of the other side. So your structure is like your CDTE is there, CDTE is there, and which is which sandwiches your HGTE. This is HGTE, these two are CDTE, like this. And then in between you have your H1 of HGTE and E1 of HGTE. Right? This is for D less than DC. Now For D equal to DC, this is critical. This is your energy. You have your CTTE, your CTE valence band. Here you have your CTTE conduction band. This will be valence band. This will be the top part of the other side, conduction band. Then we'll be having H1 and the crossing E1 and H1 at K equal to 0. So at K equal to 0, your E1 and H1 crosses. So gap closes. Now for D greater than DC. This gives inverted band. So you have energy in this axis. Here you have CDTE conduction band, CDTE valence band, E1, H1. This is now higher. This is now lower. And here E1 H1 has swept, right? And this is the region of this inverted ordering topological states that appear at the slab edges. Now for cadmium telluride wells, quantum wells basically. The experimental theoretical established critical thickness is around DC is 6.3 nanometer. Above this thickness, the well becomes inverted and the system supports the quantized Hall phase with helicalized states. This is canonical number reported in the literature for this HGT, NCT quantum wells, and below this one, it acts like a normal insulator semiconductor. So with this one, I conclude the class. If you have any question, doubt, or suggestion, you can ask in the comment section. I'll be happy to address your concern. I'll wait for 5 minutes if you have any question or doubt so that you can ask. After that, we will close the session. So I'll leave it here.